So we've been talking about pressure differentials and horizontal movement of air, and we want to take that a bit farther. We've been talking about equilibrium and making sure that high pressure and low pressure move toward equilibrium. That involves a net force. The movement from high pressure to low pressure is actually a pressure force that moves that material. So let's discuss that a bit more. When we talk about equilibrium in physics, we talk about gradients. And gradient is actually the change of a measure over the distance between those two measures. In physics, that can be a temperature or pressure, like PV equals nRT, or it can be a concentration of water vapor to air. So you see that a pressure gradient that we're talking about here is actually a change in pressure over distance. Let's explore that a bit more too. When we come back to this slide, we can look over a 100-kilometer distance between the pressures that are at 1020 millibars and 1016 millibars. And the force, the net force that moves between the high at 1020 and the low at 1016 is known as the pressure gradient force. That pressure gradient force pushes out the air from the high pressure area and pushes it into the low pressure area to bring it to equilibrium. When we look at this, we can also remember that these are isobars. Iso stands for equal, and bars stands for pressure, like barometer or barometric pressure. So we talk in terms of isobars on a map that shows distance. The isobars are usually in 4 millibar increments, and those can range from 1020 to 1016 to 1012 to 1008 to 1004, like that. You'll see them over a wide range. For instance, you can have many measurements in between the 1016 that would be here and the 1012. And you can have many measurements in between the 1012 and the 1008. And those measurements all fit in, and then you can connect the dots between the 1012 and you connect the dots between the 1008 measurements, and then all the rest of them fit in between there on a continuum. But these are for surface maps only, and surface maps deal in isobars of anything from 950 millibar pressures at the surface to 1050 pressures at the surface. Let's explore that a bit more. When we go to a surface map of the United States, we might find a line like around South Carolina here, and that's it, combining a line that matches 1020 millibars all in this line. So I might have a measurement here that's 1020, a measurement here that's 1020, one here, and one down here that's 1020. And I make a line like connect the dots. The lines are not perfect, and in fact, we make them so that we can fit in the other pressure points in between. So in here will be 1019, 1018, 1017. And then there will be a point here that's 1016, a point here that's 1016, maybe one here that's 1016, here, maybe one here that's 1016. I can connect the dots for 1016. So that's an isobaric map. And that talks about the net force that is moving between that high pressure area and the low pressure area. Now, it may not look like it's talking about the net force, but what you're looking at is the difference between a gentle gradient in some areas and a tight gradient in other areas. Let's explore that a bit more. When we talk about gentle gradients, we're talking about a change in flow over a distance, right? Because that's what a gradient is. While you have a great distance between the shores of your flow here, you'll have a large denominator. When you have a large denominator, your quotient is going to be low. There's going to be a low force here to move this water through the gap. But when you come in here, where there's a very small distance between the shores, you've got a much smaller distance here, leading to a bigger quotient or a bigger gradient force. And you will notice in here that there's a faster flow in this narrow area. Very similar to what we're looking at when we look at the maps that are isobaric maps. When we have tight gradients in here, with just a bit of distance between the lines and between the isobaric lines, we have stronger winds. And when we have a broad area between the isobaric lines, we have gentler winds in here. You might remember Sandy, and what I wanted to point out here is where the gradients are very tight in through here, not a lot of distance between the lines, the winds are much higher. You can even check them out over here. The winds are higher speed where the isobaric lines are very tight, and where the isobaric lines are broad with a lot of distance between the lines, those winds are going to be quite a bit lighter. Again, this is a surface map. And I wanted to point it out to you nationally as well, that where you find tighter gradients, you will find speeds that are higher. And where you find broader gradients, especially up in here, you're going to find winds that are lighter. Now, this map does not tell you about the speeds of the winds. This map tells you about the direction of the winds, but I wanted to give you an overall view of tight gradients versus gentle gradients. There's one last thing that I need to talk about with pressure, and that is surface altitude and how it affects surface pressures and surface maps. Now you see here, this is a beautiful day. And you might think, well, there's not a cloud in the sky, it's a beautiful day. That would probably be at a pressure of about 1010 to 1020 or so. But you see here on this surface up here at sea, you get this really low pressure of 894. That low pressure of 894 would be the worst hurricane of the century. But it's at the surface on a beautiful day. And what you're seeing is that there's a very dramatic change in pressure over altitude. Remember our graphs that looked at temperature and altitude. That temperature change was very steep as altitude increased. So in doing that, we have to correct for changes in a vertical pressure. And we have to do that in order to see the differences on an even playing field on a surface map. The way we change and correct for those pressures is to look at the altitude. This altitude is at 1100 meters. And we say to ourselves, okay, for every 10 millibars of altitude, I'm going to add 1 millibar of pressure. So what you do when you look at the altitude here, you just take off 10 and you say, okay, I will add in 110 millibars of pressure for 1100 meters of altitude. So I just divide by 10 and I put and add on that 110 millibars of pressure. So when I add 110 millibars of pressure to 894 millibars, I'm actually getting 1004 millibars, which is a really fair weather pressure. And I can compare it to other pressures right at the surface at 1000 millibars. And I can compare it to other pressures that I have also corrected from altitude. This altitude was 300 meters. I added 30 millibars. This altitude was 600 meters. I added 60 millibars. And when I add 60 millibars, I added to the altitude millibar. 962 plus 60 equals 1012 millibars. So this is a way of leveling the playing field at the surface. You add 1 millibar for every 10 millibars in altitude. Finally, there is a force opposing the pressure gradient force, and that force is friction. It opposes the horizontal net force, and it opposes it across the entire vector. It opposes it in terms of speed and in terms of direction. I think the speed is easy for you to understand. The direction is that it takes the path of least resistance. If you looked at that photo, it would not take the path, it would not take the wind through the path around the trees. It'll take the wind through the path around the stream because that has less resistance to it. The trees add friction. I hope this helps you out. I'll talk to you on the other side.